Very good morning to everyone. Welcome back to the course on advanced hydraulics. We are on the lecture 6 of this course. We are on the first module of this particular course itself. Let us continue with the discussion as was held in the last class. Last class we have discussed on energy equations. For open channel flow, what is meant by energy, how the energy is computed and all, they were discussed in the last class. Energy was represented in terms of head, or you can say energy per unit weight of liquid, like that this was represented. We have even mentioned the conservation of energy. We had represented energy, total energy at any channel section. Say if any channel section is there, arbitrary channel section is there. Then the total energy is represented as H. This consists of your velocity head, and it consists of your pressure head, it constitutes your datum head, and all these three components, that gives you what you mean by the total energy at a channel section. So these were given. We had normally, as we suggested, that in civil engineering we are dealing with channels of negligible slope, then we can give the following thing as y is equal to z plus depth of flow y plus alpha v squared by 2g. Like this we had specified that in our last class. We have even suggested that between two sections, say if this is section 1 section 2 and flow, if the flow direction is in this right side, then the total energy at section 1 and total energy at section 2, they differ by a quantity what is defined as the head loss or the energy lost. It is always that the energy will be lost. It cannot be gained in the total energy, can never be gained from fluid flowing from one direction to other. So this was also suggested between two sections. We had even suggested that H1 is equal to H2 plus del HL, where your del HL or the head loss the head loss can be computed from friction loss and eddy loss. We also suggested that in the prismatic channels eddy losses are negligible, and most of the case your head loss is approximately same as the head loss due to friction. Subsequently, we suggested if your energy correction coefficient alpha approximately if it is 1, then H1 is equal to H2 plus del HL can be given as Z1 plus V1 squared by 2G plus Y1 is equal to Z2 plus V2 squared by 2G plus Y2 plus the friction, the loss of head due to friction. Like this we had suggested, and if the loss of head due to friction is approximately 0, then we subsequently suggested that at any two sections the total energy will be same and this is same as your Bernoulli's equation. So, please note that if the head loss due to friction is negligible, then you are getting relation between the energy equation relation in the following form. This is same as your Bernoulli's equation. Today, we will be just going to deal with a new concept called specific energy. You know, means the total energy at any section H is equal to datum head plus velocity head plus depth of flow or pressure head, you can tell like that. Subsequently, but you have seen that this is for channels of small slope and alpha approximately equal to 1. The specific energy, it is defined as, I will just write it down here, the amount of energy expressed in terms of head and is the energy per unit weight of liquid at any section of the channel measured with respect to the channel bottom. Measured with respect to the channel bottom. We can define in the following form. So, what do you mean by this definition? You have seen for any channel at a height z from the datum line and depth of flow y and velocity head v squared by 2g, the total energy as given is H is equal to the following form. Now, the specific energy is the amount of energy in terms of head and is the energy per unit weight of liquid at any section of the channel measured with respect to the channel bottom. Now, instead of taking your datum line, now if I consider the channel bottom and if you measure the energy per unit weight now, that is the specific energy of the channel section. And that is quite an important parameter now in the open channel flow. You will see from here onwards that is one of the most important terms, specific energy, which will govern the fluid flow in open channels. So, we will see as per the definition now you can easily define the term specific energy is equal to y plus v squared by 2g. So, that is nothing but the summation of your depth of flow and velocity head. So, specific energy at any channel section. So, you should note that if this is not a prismatic, if it is not a prismatic channel, or if the section of the channel varies with respect to length, then you can measure specific energy at specific locations only, or at specific sections. So, at each section your specific energy values may be different. Let us define specific energy in the following form. So, for any arbitrary cross section, you can use the following form: E is equal to y plus v squared by 2g. Of course, we are dealing with the small sloping channels, or where the slope of the channels are not significant, and alpha, that is energy correction coefficient, is approximately 1. In those situations, we can use the following form: if alpha not equal to 1 and if your slope is significant, then your E has to be given as y cos squared theta plus alpha v squared by 2g. But in our analysis, let us follow the same thing. For a given discharge from any cross section of the channel, for a given discharge, you know that the discharge can be represented as the area of the cross section into average velocity. This is from your old physics itself, you have understood them. Or you can now suggest that the average velocity is nothing but q by a. Substitute this quantity here. Your specific energy now becomes y plus q squared by 2g a square. So, however, you know that the area of the cross section A, this is a function of depth of flow y. That is quite clear, isn't it? So, now you are getting energy, the specific energy, now you are getting it as some function of y and discharge q. Once you understand that the specific energy is now function of depth of flow and discharge, you can easily compute, that is, if the depth of flow and q is given, you can easily compute specific energy, or specific energy is a function of the following parameters. We have to see how specific energy is now affected by these parameters. As we are dealing with open channel hydraulics, mostly regulated flow is there. In canals, whether it be in canals, whether it be in channels, or whether in some of the rivers and all, it is regulated flow. So, most of the time your discharge is known, your discharge q is a known quantity, or you can regulate q. So, if you keep q as a constant, then you will see that your specific energy is now only function of depth of flow y. So, for any given cross section, you can maintain the same discharge q, but you will see that for the same discharge q, if the depth varies, then the corresponding velocity term varies. That is how you can keep the discharge constant in any given cross section. So, then in that case E is equal to function of y. 2g a square. So, q is a constant term here. So, this becomes only function of y. You can easily plot now E versus depth of flow. That is, how if the depth of flow in any given cross section, if it varies, how the specific energy term varies, that can now be easily plot. You can plot them. We will see. Say okay, we will just give it in an example form, that will give you a better idea now. If you try to plot them, this is not an example, this is just for any arbitrary cross section of the channel. You can plot on the y axis the depth of flow, you can plot on the x axis the specific energy term. This particular curve E versus y will now look in, it will be now in the following form. This is the form of the curve E is equal to y plus q squared by 2g a square, where q is a constant. That is, for any particular q, for any particular discharge value, you can easily plot E versus y and you will get the following form of curve. How are you sure that the curve will be of the following form? You know that this is a nonlinear relationship. E is now related with y only, but it has a nonlinear relationship with y. Therefore, this particular curve is also a nonlinear curve. How are you sure that it can be of the following form only? Take an example of for example, let us take a rectangular channel. Its breadth B is equal to 2 meters. So, you have your depth of flow, arbitrary depth of flow. Let us suggest that a constant discharge Q is equal to 4 meter cube per second is occurring to the cross section of this rectangular channel. Now, you can suggest that the area of cross section is B into y, that is 2y, right. Your specific energy E is equal to y plus q squared by 2g a square. What will be that for the rectangular cross section? Y plus q is given as 4 squared by 2 into 9.81 into a, that is 2y whole square. On simplifying the terms, you will see that this is 0.204 y square. In this relationship, for this particular rectangular channel, now increment this relationship. Now, it is sure that at y is equal to 0, when there is no depth of flow, this relationship is not valid. And of course, when there is no depth of flow, that means water is not there in the channel, and we are not interested in those cases. We are dealing with when the flow exists in the channels. For those conditions where y not equal to 0, the specific energy relationship we have in the following form. Start with a very small value of y, say y is equal to 0.1 meter onwards. Let us start and increment y, in 0.1 meter steps. Just try to plot them or just try to compute them. For example, when y is equal to 0.1 meter, your specific energy term, this you will get it as 0.1 plus 0.204 by 0.1 square. You just calculate them. I am getting the full thing as 20.5 meter. You see now, when the depth of flow in the rectangular channel, if it was 0.1 meter, a very low depth, the specific energy computed was 20.5 meter. You can just plot them. For the same rectangular channel, this is depth of flow, this is specific energy in the x axis. You can just plot that. Say E is equal to 20, say okay, let it be here. When y is equal to 0.1, then when y is equal to 0.2 meters, you are getting E is equal to 0.2 plus 0.204 by 0.2 whole square. This is around 5.3 meter. So, your specific energy is reducing now. You see, when this was 0.1, this is 0.2 and your specific energy is somewhere here, or you just extend it somewhat here, then compute it in the similar form. When y is equal to 0.3 meter, what is the corresponding E? I am getting it as 2.56. Okay, I can just give it in a tabular form. Can just give this as a tabular form, y depth of flow and the corresponding specific energy. So, when both of them are in meters, so 0.1, this is 20.5, 0.2, this is 5.3, 0.3, this is 2.567, 0.4, 1.675, 0.5, 1.316, 0.6, 1.167, 0.7, 1.116, 0.8, 1.119. You see that after 116 it is just started increasing now. 0.9, 1.152, 1.204, like that you can go on computing with respect to any depth of flow what is the corresponding specific energy, and if you plot them you will get the curve in the following form. This is something of the following nature you will get. So, this is up to you to do that. We just gave that how the specific energy curve looks like for any cross section, any cross sectional. So, the same pattern is available for any cross section irrespective of whether it is a rectangular channel or whether it is a triangular channel or whether it is an arbitrary cross sectional channel. For any cross sectional, you will get the specific energy curve in the following form. So, what do you understand from that? If you look into this specific energy curve, that is E versus Y, let us now take the general case. For any arbitrary cross sectional channel, let this be the specific energy curve E versus Y. Now, for any specific energy or any point in this specific energy, say this is P, its corresponding y axis value will give you the depth of the flow in that region, and the corresponding x axis will give you the specific energy of the flow. Now, just take it, say for any particular value, you just extend this one. If I give this as E1 or E at this location, for the same specific energy magnitude of E1 or EI, any term you can give, this is just to represent that the magnitude of energy here. You are now observing two depths of flow, say one here and one here. Let me give this as y1 and y2. That is, you are observing two different depths of flow for same magnitude of energy. So, the depth of flow y1 and y2, see y1 is low stage or lower depth, y2 is high stage or higher depth. So, you can see such two depths for any value of E, for any value of specific energy for a particular discharge. Of course, for a particular discharge, for any value of E, you will see two depths of flow, that is y1 and y2. One is the lower stage and one is the higher stage. They are called alternate depths. They are mutually called alternate depths of flow. That is, for same specific energy, you have two depths of fluid flow. The difference between y1 and y2, it may decrease as you proceed from lower to slowly to the left side. If you proceed, it may decrease initially, then it will increase gradually. So, that shows that at a particular location, as you proceed, as you decrease the specific energy further, there reaches a point in the curve, where there is only one depth of fluid flow. There are no two alternate depths, only one depth of fluid flow is there for that particular specific energy for a given discharge. This particular energy, this particular energy and this particular depth, they are classified as critical flow conditions. So, please note that the depth or the specific energy, when you reduce the specific energy gradually, a point will be reached where both the depths coincide, that is, both the alternate depths coincide. that is the minimum specific energy available, and beyond that the specific energy will increase further. So, the minimum specific energy where there is only one flow of depth, where there is only one depth for the fluid flow, that is called critical flow condition, and that energy means that specific energy is minimum in critical flow condition. That depth is also called critical depth. Okay. So, I can just write this as YC, critical depth of fluid flow. So, what do you understand by critical depth of fluid flow? In the critical depth or in the critical flow condition, there will be minimum specific energy, that is the specific energy will be minimum for a given discharge Q in critical flow conditions. So, let us infer from this. You know E is equal to y plus v squared by 2g, or E is equal to y plus q squared by 2g a square. For critical flow conditions, what do you observe here? For critical flow conditions, you will observe that the two alternate depths y1 and y2, one will be below the critical depth, one will be above the critical depth. So, the YC which is given as the critical depth, whatever flow occurs or whatever fluid flow is there, say for any arbitrary specific energy E1, it was having two alternate depths y1 and y2. Y1 is less than yc, therefore, as discharge is constant, the velocity will be higher in this situation, whereas y2 is greater than yc, velocity will be less in this situation. So, the y1 depth condition, it is called supercritical flow, and y2 depth condition, it is called subcritical flow. That is mainly regarded to the velocity. At the critical depth, velocity will be in critical condition or the flow will be in critical condition. Whatever flow occurs or depth of flow, if it is greater than the critical depth, then the velocity will be less than the critical flow velocity. Therefore, it is called subcritical flow condition. When the depth of flow is less than the critical depth, velocity of the flow will be more. Therefore, we can suggest that as a supercritical flow condition. What are the criterion for critical flow conditions? Just let us look this into the mathematical form. For critical flow condition, your specific energy should be minimum for a given discharge. That is what we have identified from this particular curve. That means dE by dy should be equal to 0. Just try to do that. You know dE by dy. So, this is 1 minus q squared by g a cube into dA by dy. Just consider a top element. Its depth is dy elemental depth is dy, top width is T, and that elemental area is given as T into dy, or dA by dy can be suggested as the top width of the flow also. Let us substitute it here. So, you will get d by dy is equal to 0 is equal to 1 minus q squared by g a q into T. So, for the critical flow condition, the corresponding terms will be related in the following form, or you can suggest here again 0 is equal to 1 minus q squared by g, that area whatever will be measured or computed, that will be critical flow area, and whatever top width will be computed, that will be the top width computed in critical condition Tc. Like that we can just give as a suffix for the top width and area. This implies q squared by g is equal to AC cube by Tc. This is one relation or one condition that suggests critical flow condition, or for critical flow condition the following relationship should hold good. Please note that this is only for the critical condition, the following terms hold good. You can again rearrange the terms here. You can rearrange the terms in the following form also. I will just give it here. In this relationship, 1 minus, let me take this as v squared by g into T by A is equal to 0. That is, you can suggest that v squared by g, if you recall the term A by T that was suggested earlier, that is area of flow by T, that was defined as your hydraulic depth d. This should be equal to 1, or beg pardon, this is v squared by g d. So, this d is in critical condition. So, dc, let me give it as critical hydraulic depth in critical condition, critical state of flow. So, v squared by g dc is equal to 1. Or you can suggest that v squared by 2g is equal to dc by 2. This is just a physical, it is to note that your velocity head is equal to half of your hydraulic depth. This, like this you can study, you can understand the concept in such a way that in critical state condition your velocity head is equal to half of your hydraulic depth. Similarly, this can be again rearranged, v squared by g dc is equal to 1, it was suggested, or this can be given as v squared by root of g dc is equal to 1. If you recall of one of our earlier explanations also, this quantity v by root of g dc, this can be defined as Froude number. You can define the left hand side of this particular relationship as Froude number, and Froude number For critical flow condition, it should be always 1. For critical flow condition, the fluid number should be always 1. If fluid number is less than 1, if fluid number is greater than 1, what does that imply? See, fluid number greater than 1 means the velocity should be greater. That implies supercritical flow. Fluid number less than 1 means velocity should be less. That implies subcritical flow. So, these are the criterion for critical flow conditions. So, we have seen that for critical flow conditions, your fluid number this should be 1, or you can give the other relationship V squared by 2G is equal to half of your hydraulic depth, or you can specify Q squared by G is equal to AC cube by TC. Like this, these are some of the criterion you can use for critical flow condition. We suggested and we have derived it. What happens if your channel slope, if channel slope is or channel bed slope is significant, and if alpha, that is the energy correction coefficient, if this is not equal to 1, if such situation exists, how can you define the critical flow conditions? Please do this as assignment. Now, this is up to you to do as an assignment, how to define the critical flow conditions for a channel section whose bed slope is significant and the energy correction coefficient is not 1. For such a condition, how you can define the critical flow condition in a similar form? It is up to you to do that. You complete that as an assignment. We had suggested for same discharge Q, how your specific energy curve looks. This was just discussed few minutes ago. We suggested that E is equal to y plus Q squared by 2G A squared. Here this E is only function of y. We are stating this for a constant discharge condition in a channel section. What happens if you are varying the discharge in the channel section, any arbitrary channel section? If you are varying the discharge quantity, how will your specific energy curves look like? As from this relationship, you know, for a particular discharge Q, you will get a specific energy curve in the following form. You can draw now arbitrary curves, say for different values of Q, Q1, Q2, Q3, different values of Q, you can get different specific energy curves. Maybe say Q1 is less than Q2, less than Q3. Like this, if you want to draw the curves, then the following specific energy curves will look in the following form. say this is for Q1, this is for Q2, for Q3, Q4. So, you have not asked me how I can draw, how do I know that Q1, the specific energy curve of Q1 is like this, specific energy curve of Q2 is like this, for Q4 it is like this. You have to adopt the same principle. We have done how to compute or how to compute the specific energy for a same discharge condition in a rectangular cross section. You have already done that. Similarly, you now vary the discharge. You just give, say, in the same condition, same problem itself, you just vary the discharge. Instead of 4 meter cube per second, now use 2 meter cube per second, then you use 6 meter cube per second, then you use 8 meter cube per second. Subsequently, you will see that the specific energy curve means for which discharge is minimum, that curve will be shown like this. Q1 is having the least discharge, Q2 greater than, means Q2 is greater than Q1, Q3 is greater than Q2, Q4 is greater than Q3, like this you will get the specific energy discharge. It is up to you to do it, work it out and find the proof. We are not going to discuss, we have already done for a simple case earlier, you have to analyze it on your own. So, if you can plot it in the following form, what do you infer from the figure now? E versus Y here. If I give any particular, if a person happens to go through, say, any particular arbitrary specific energy, he just observed that there is a specific energy value here E1. If a straight line is plotted, he will get different types of alternate depths. Say, for the discharge Q1, he will get the corresponding alternate depths. For discharge Q2, for the same magnitude of energy, for different discharge, he will get different type of alternate depths. This is a curious, means you can analyze that from the same channel section. If so and so discharge occurs, this will be the alternate depths or this will be the depth of flow, like that you can visualize now. These curves suggest those parameters or those properties. So, it will be very good to analyze the things, channel properties and all, it will be very good to understand those things. Say here, if I look at here, Q3, for the discharge Q3, the depth is like this, and for the discharge Q4, you will see that the depths are so and so. You will reach a particular point. These curves can be further elaborated. Like this, on increasing the values of Q, these curves will go on Q5, Q6 and all. So, you will see that this energy, specific energy, whatever magnitude of specific energy you have taken as of interest, that will become a critical energy condition or critical flow condition when it is, this will become the critical flow condition for a particular case. If I just draw the curve properly here, this becomes a critical energy, or it will become this energy will become condition for critical flow only for a particular situation. So, if that curve happens to be somewhere here, let us suggest that. you can now identify the corresponding discharge, isn't it? Can't you identify the corresponding discharge? If you are given, if you are specified of the magnitude of specific energy, then this magnitude of specific energy can determine a particular flow where critical flow condition occurs. You can identify that from the following curves. You have to interpret them. How do you interpret them? Use the same mathematical analysis now. E is equal to y plus q squared by 2g a square. So, now in this case what you are doing? You have specified E. E is not a variable now. If you have specified E, what is y, what is q, or what is a? Let us see that now. Your analysis, it can be given in the following form. I can write the relation of q now. Q is equal to root of E minus y into 2g, the whole quantity multiplied by the area of cross section. What does this suggest now? For the given flow condition, if it has to be a critical flow condition, what could be your magnitude of q? How will you understand that? Let me ask you here. Here the Q5 specific energy curve is going like this, Q6 is going like this. Do you think that those discharges have any influence on the specific energy term here? They are not having any influence. You see this lines mark, means as this lines goes on, the specific energy curves for Q5 and Q6 are on the right side. It is not having any influence. That is, it is not having any depth of flow. Means this particular energy is not determining any alternate depths for Q5 and Q6 and for higher magnitudes of discharge. So, it is not having any influence on the discharge there. However, the same magnitude of energy, it is determining alternate depths for discharges which are less than Q5 or whichever are less than this particular value of Q, which we do not know. So, that means whatever are on the left, they are having less discharge, and this is the point where maximum discharge occurs. Can you understand? This is the point where for the given energy maximum discharge occurs. Suggest that relationship here. So, dq by dy will be equal to 0 for the maxima condition. dq will be dy for the maxima condition. You see what will be your relationship now? So, this will be equal to 2g e minus y of root dA by dy minus GA by so if this quantity is 0, this is T, you know that. I will get the following relationship now, same, that is q square T by GA cube is equal to 1. The same relationship was identified when you determine the flow, means depth of flow condition also, isn't it? So, that means for a given specific energy, maximum discharge occurs when the flow is in critical condition, right, or for a given discharge q, the minimum specific energy for that given discharge q, that will determine the critical flow condition. So, that is quite means it is a quite good relationship which you can infer and further analyze the fluid flow in open channels and all. Based on to continuing with these lectures and all, in the next class we will determine what are the other things, what are the things that suggest for the specific energy, related to specific energy, some of the other concepts that come into picture and all, we will be discussing them. We will also be conducting the quiz for the today's topic in the same series. So, let us wind up today's lecture. Thank you.